Welcome to our deep dive into Gibbs Free Energy, a fundamental concept in chemistry and thermodynamics. Today we'll explore what Gibbs Free Energy is, why it matters, and how it helps us predict the direction of chemical reactions. Whether you're a student, a science enthusiast, or just curious about how the world works at a molecular level, this journey will clarify the mysteries behind spontaneous processes and energy changes. Let's begin by understanding the basics and setting the stage for the fascinating details ahead. Gibbs free energy, often represented by the symbol G, is a thermodynamic quantity that combines enthalpy, entropy, and temperature to predict whether a chemical reaction will occur spontaneously. It's named after Josiah Willard Gibbs, an American scientist who made significant contributions to physical chemistry. The concept helps chemists and engineers understand which reactions can happen on their own and which require external energy. By calculating changes in Gibbs free energy, we can determine the feasibility of processes in everything from batteries to biological systems. The equation for Gibbs free energy is central to understanding its role in chemistry. It's expressed as G equals HT asterisk S, where H stands for enthalpy, T is temperature in Kelvin, and S is entropy. This equation elegantly ties together the heat content of a system, the disorder within it, and the temperature at which the process occurs. By plugging in values for enthalpy and entropy, scientists can predict if a reaction will proceed without outside help. This formula is a cornerstone in both theoretical and practical chemistry. Enthalpy, symbolized as H, represents the total heat content of a system. It's a measure of the energy stored within chemical bonds and is crucial for understanding how much energy is absorbed or released during a reaction. When a reaction releases heat, it's called exothermic, and when it absorbs heat, it's endothermic. Enthalpy changes are a key part of the Gibbs free energy equation, helping us see how heat flow influences whether a reaction is favorable or not. Entropy, denoted as S, measures the degree of disorder or randomness in a system. In chemical reactions, entropy reflects how molecules are arranged and how much freedom they have to move. An increase in entropy means greater disorder, which often favors spontaneous reactions. Entropy is a driving force in the Gibbs free energy equation, showing that not just energy but also the arrangement of particles determines if a process will occur naturally. Temperature, represented by T in the Gibbs equation, plays a crucial role in determining the spontaneity of a reaction. As temperature increases, the impact of entropy on the overall free energy chain becomes more significant. This means that some reactions that aren't spontaneous at low temperatures can become spontaneous at higher temperatures, simply because the entropy term outweighs the enthalpy. Understanding this relationship helps chemists control reactions in the lab and in industry. Key use of Gibbs free energy is predicting whether a reaction is spontaneous or non-spontaneous. If the change in Gibbs free energy, delta G, is negative, the reaction occurs spontaneously. If delta G is positive, the reaction requires energy input to proceed. This simple rule allows chemists to quickly assess the likelihood of a reaction happening under given conditions, making it a powerful tool in both research and industry. Let's look at a real-world example: the melting of ice. At temperatures above 0 degrees C, ice melts spontaneously. Here, the increase in entropy as solid water becomes liquid outweighs the enthalpy required to break the bonds in ice. The negative Gibbs free energy change at these temperatures explains why ice melts naturally on a warm day, illustrating how the equation applies to everyday phenomena. Photosynthesis is a classic example of a non-spontaneous reaction. Plants convert carbon dioxide and water into glucose and oxygen, but this process requires energy from sunlight. The positive Gibbs free energy change means the reaction won't happen on its own. Instead, plants harness solar energy to drive the process, showing how living systems use external energy to create order and store chemical energy. Cellular respiration is the opposite of photosynthesis and is a spontaneous process. Here, glucose and oxygen are converted into carbon dioxide, water, and energy. The negative Gibbs free energy change means cells can extract energy from food without needing extra input. This energy powers everything from muscle movement to brain activity, highlighting the importance of Gibbs free energy in biology. Batteries are another practical application of Gibbs free energy. When a battery discharges, chemical reactions inside release energy, which is harnessed to power devices. The negative Gibbs free energy change in these reactions ensures that energy flows from the battery to your phone or flashlight. Understanding these principles helps engineers design more efficient and powerful batteries for everyday use. In industry, controlling Gibbs free energy is crucial for maximizing efficiency and minimizing waste. Chemical engineers use the concept to design processes that favor spontaneous reactions, reducing the need for costly energy inputs. By optimizing temperature, pressure, and reactant concentrations, industries can produce chemicals, fuels, and materials more sustainably and economically. Gibbs free energy isn't just about spontaneity, it also helps predict the direction in which a reaction will proceed. By calculating delta G for both forward and reverse reactions, chemists can determine which pathway is favored under specific conditions. This predictive power is essential for designing experiments and manufacturing processes that yield the desired products. Standard Gibbs free energy change, denoted as delta degrees, refers to the change in free energy when reactants and products are in their standard states, typically 1 atmosphere of pressure and 25 degrees C. This value provides a reference point for comparing different reactions and is widely used in tables and databases. Knowing the standard values helps chemists quickly assess the feasibility of reactions under typical conditions. Most real-world reactions don't occur under standard conditions. Factors like pressure, temperature, and concentration can shift the Gibbs free energy change, making a reaction more or less favorable. Chemists use modified equations to account for these variables, ensuring accurate predictions in the lab and industry. This flexibility makes Gibbs free energy a versatile tool for understanding complex systems. At equilibrium, the change in Gibbs free energy is zero. This means there's no net change in the concentrations of reactants and products, and the system is stable. The relationship between Gibbs free energy and equilibrium constants allows chemists to calculate how far a reaction will proceed before reaching balance, providing valuable insights for both research and industry. Catalysts speed up chemical reactions without changing the overall Gibbs free energy change. They work by lowering the activation energy, making it easier for reactions to occur, but they don't affect whether a reaction is spontaneous. This distinction is important in both natural and industrial processes, where catalysts are used to increase efficiency without altering the fundamental thermodynamics. Biological systems rely heavily on Gibbs free energy to drive essential processes. From muscle contraction to nerve impulses, cells use the energy released from spontaneous reactions to power life. Enzymes, which are biological catalysts, help control these reactions, ensuring that energy is released or stored as needed for survival and growth. Adenosine triphosphate, or ATP, is often called the energy currency of the cell. When ATP is broken down into ADP and phosphate, it releases a significant amount of Gibbs free energy, which cells use to perform work. This process is a prime example of how living organisms harness and manage energy at the molecular level. Cells often couple non-spontaneous reactions with spontaneous ones to drive essential processes. By linking a reaction with a positive Gibbs free energy change to one with a negative change, the overall process becomes feasible. This strategy is vital for metabolism, allowing organisms to build complex molecules and maintain order in a constantly changing environment. Medical science uses Gibbs free energy to understand drug interactions, metabolic pathways, and disease mechanisms. By analyzing the energy changes in biochemical reactions, researchers can design more effective treatments and predict how drugs will behave in the body. This knowledge is crucial for developing new therapies and improving patient outcomes. Gibbs free energy plays a role in environmental science as well. It helps predict the fate of pollutants, the efficiency of waste treatment processes, and the feasibility of renewable energy technologies. By understanding the energy changes involved, scientists and engineers can develop cleaner, more sustainable solutions for environmental challenges. Renewable energy technologies such as fuel cells and solar panels rely on Gibbs free energy to assess efficiency and performance. By analyzing the free energy changes in these systems, engineers can optimize designs and improve energy conversion rates. This understanding is key to advancing clean energy and reducing our reliance on fossil fuels. Food scientists use Gibbs free energy to study cooking, preservation, and digestion. By understanding the energy changes during chemical reactions in food, they can develop better preservation methods, improve flavors, and ensure food safety. This knowledge also helps explain why certain foods spoil or change texture under different conditions. Materials scientists rely on Gibbs free energy to design new alloys, polymers, and ceramics. By predicting which reactions will occur during processing, they can create materials with desired properties for construction, electronics, and more. This predictive power accelerates innovation and leads to stronger, more durable products. Geologists use Gibbs free energy to understand mineral formation, rock transformations, and the movement of elements within the Earth. By analyzing energy changes in geological processes, they can predict where valuable resources might be found and how landscapes evolve over time. This knowledge is vital for resource management and environmental protection. Space scientists apply Gibbs free energy to study chemical reactions on other planets, the formation of atmospheres, and the potential for life beyond Earth. By understanding how energy changes drive reactions in extreme environments, researchers can better interpret data from space missions and plan future explorations. Corrosion, the gradual destruction of materials by chemical reactions, is influenced by Gibbs free energy. Engineers use this concept to predict which metals are most likely to corrode under certain conditions and to design protective coatings that prevent damage. This helps extend the lifespan of structures and reduce maintenance costs. Environmental engineers use Gibbs free energy to design processes for cleaning up pollution. By understanding which reactions are spontaneous, they can select the most effective methods for breaking down contaminants and restoring ecosystems. This approach leads to safer, more sustainable cleanup strategies. Agricultural scientists apply Gibbs free energy to optimize fertilizer use, improve crop yields, and manage soil health. By predicting how nutrients react in the soil, they can develop strategies that maximize plant growth while minimizing environmental impact. This knowledge supports sustainable farming and food security. Nanotechnologists use Gibbs free energy to design and control reactions at the nanoscale. By understanding how energy changes affect tiny particles, they can create new materials and devices with unique properties. This field is opening up exciting possibilities in medicine, electronics, and energy storage. Electronics engineers use Gibbs free energy to design semiconductors, batteries, and other components. By predicting which reactions will occur during manufacturing and operation, they can improve device performance and reliability. This understanding is crucial for advancing technology and meeting the demands of modern life. Art conservators use Gibbs free energy to understand the chemical reactions that cause artwork to deteriorate. By predicting which processes are spontaneous, they can develop preservation techniques that slow down damage and extend the life of priceless pieces. This blend of science and art helps protect cultural heritage for future generations. Climate scientists use Gibbs Free Energy to model atmospheric reactions, predict greenhouse gas behavior, and understand energy flows in the environment. This knowledge is essential for forecasting climate change and developing strategies to mitigate its effects. By analyzing energy changes, scientists can make more accurate predictions about our planet's future. Pharmaceutical researchers use Gibbs Free Energy to design new drugs and predict how they will interact with biological targets. By understanding the energy changes involved, they can create more effective and safer medications. This approach accelerates drug discovery and helps bring life-saving treatments to market faster. Educators use Gibbs Free Energy to teach students about the principles of thermodynamics and chemical reactions. By providing real-world examples and hands-on experiments, they help learners grasp complex concepts and appreciate the role of energy in everyday life. This foundation is essential for future scientists and engineers. Gibbs Free Energy isn't just for scientists, it affects our daily lives in countless ways. From the food we eat to the batteries in our devices, understanding energy changes helps us make better choices and appreciate the science behind ordinary phenomena. This awareness can inspire curiosity and a deeper connection to the world around us. While Gibbs Free Energy is a powerful tool, it has limitations. It doesn't account for reaction speed or kinetic barriers, meaning a reaction might be thermodynamically favorable but still occur very slowly. Understanding these limits helps scientists choose the right tools and methods for studying and controlling chemical processes. Reaction kinetics, or the study of reaction rates, complements Gibbs Free Energy by explaining how quickly reactions occur. Even if a reaction is spontaneous, it might need a catalyst or specific conditions to proceed at a useful rate. Combining thermodynamics and kinetics gives a complete picture of chemical behavior. Researchers across disciplines use Gibbs Free Energy to design experiments, interpret data, and develop new theories. Its predictive power makes it a cornerstone of scientific inquiry, guiding discoveries in chemistry, biology, physics, and engineering. This broad applicability underscores its importance in advancing knowledge. Innovation often starts with understanding the fundamental principles of energy and matter. Gibbs Free Energy provides a framework for inventing new technologies, improving existing processes, and solving complex problems. Its influence can be seen in everything from green energy to advanced materials and medical breakthroughs. As science and technology progress, Gibbs Free Energy will remain a vital tool for understanding and shaping the world. From tackling climate change to developing new medicines, its principles will guide future discoveries and innovations. Staying curious and informed about this concept will empower us to make smarter decisions and create a better future. Let's recap what we've learned about Gibbs Free Energy. It's a thermodynamic quantity that predicts whether reactions are spontaneous, helps design efficient processes, and has applications across science and industry. By understanding enthalpy, entropy, and temperature, we can make sense of the energy changes that drive the world around us. If you're interested in learning more, consider exploring advanced topics like non-equilibrium thermodynamics, statistical mechanics, or the role of Gibbs Free Energy in quantum chemistry. These fields build on the concepts we've discussed and open up new frontiers in science and technology. Thank you for joining us on this journey through Gibbs Free Energy. We've seen how this powerful concept connects chemistry, biology, industry, and everyday life. By understanding the principles behind energy changes, we can appreciate the beauty and complexity of the natural world and harness its potential for progress.